Hey everybody, so we're moving on to the next chapter, and the title of this chapter is called VSEPR. It stands for Valence Shell Electron Pair Repulsion Theory. Um, and basically what this theory tells you about is what the shapes of molecules are. And it's an extremely accurate theory for how simple it is. And what's kind of neat about it is that we're kind of continuing on this theme of going from fundamental properties of the universe, right, in quantum mechanics, to then explaining properties of the elements and now properties of molecules, right? And we saw that in last chapter with the structure of molecules. And now we're going to take from those structures of molecules, we're going to be able to predict fairly accurately, very accurately in most cases, their shape. So let's get started with the slides. So why is shape important? Well, a lot of different reasons other than just being interesting. One thing is that, the structure of a molecule is a big factor in determining its properties and its function, right? So you think about designing a drug, or think about the function of an enzyme, or DNA, or anything in biology. The structure determines in a large part how it works, right, and what its properties are. So incredibly important for a wide range of fields, not only within chemistry. Okay, and so I mentioned there's what we're going to be talking about is this VSEPR theory. You don't really need to know this acronym. It's one of those things that it's just easier to kind of see through examples. So we're going to be predicting the shape of molecules, and the whole theory behind this approach is that you have pairs of valence electrons. We saw that in all of our Lewis structures, right? Except for at the very end of last chapter, we went over odd number of electrons, where we had a singly unpaired electron. But in general, we had even pairs of number of electrons, and that put everything in pairs. And regardless of the total number of electrons, there was always, or in a lot of cases, there are what we call lone pairs, right? So you have pairs of valence electrons that are in bonded atoms, and those are going to repel one another. And basically, because there's electrons in those bonds, okay, since electrons are negatively charged, if you have two bonds close to one another, that's going to be unfavorable. So these two bonds, those bonding electrons are going to try to get as far apart from one another. They're going to repel one another as possible. And so that's the basis of this theory. If you can understand that basic principle that electrons are going to try to be as far apart from one another as they can, you'll be able to understand this, I think, quite well. So we have to we're talking about electron repulsion here, so we have to just talk about the different types of electrons that there are. I mentioned there's lone pairs, right? Those are the pairs of electrons that aren't involved in a bond. And then there's bonding electrons. And for our purposes in this course, a bond represents or contains two electrons always, okay? In more advanced chemistry courses, that's not always true, but most of the time that's true. And so that's how we're going to think about it. A bond contains two electrons, all right? And so I'm going to define something that's just in the slides. The book doesn't call it this, okay? But I call it this because I think it helps differentiate things. I'm defining something in red there called steric number. And that's going to be defined as the number of lone pairs plus the number of bonds, okay? So let's look at these two structures. I have the Lewis structure of water drawn out and the Lewis structure of carbon dioxide drawn out using our rules, the octet rule, right, for most of the elements, and the duet rule for hydrogen. We could come up with these structures, and calculating the total number of valence electrons would be as part of that calculation. I hope you can do that by now. But there's the Lewis structure for water. And so what would the steric number be? Well, there are two lone pairs and there are 1, 2 bonds, okay? And it's really a number of bonding sites, as you'll see. It doesn't matter if it's a single bond or a double bond, you count that as one, okay? So it's number of bonding sites is the way to think about that. And so, you know, just to be really clear, let's just change this to, you know, bonding sites. And why am I saying that? Okay, so here steric number is 4. There's 2 lone pairs, 1, 2, and then 2 bonding sites. So total steric number is 4, 2 plus 2. Here, okay, the steric number is 2. Why? Carbon, this is a central atom. We're looking at the central atom here to determine this. Has 1 bonding site here, 1 double bond, and another double bond there. So the steric number there is 2, okay? So if you can get the steric number, you'll be a long ways to figuring out this VSEPR theory. So how are we going to predict shape? Well, the first thing is doing all the work from the last chapter, which you have to draw the correct Lewis structure. Once you do that, then you're going to determine the steric number of the central atom. You're then going to arrange the electrons and atoms around the central atom so that they are as far apart as possible, okay? Then you're going to determine the steric geometry, okay? And from that, you're going to determine the shape of the molecule, and I'll tell you the difference between those later on. And if you want to, you know, maybe the question might ask you whether or not the molecule is polar. That would mean it has a permanent dipole in it, has a minus end and a positive end, or if it's nonpolar, okay? And so let's end this video here, and we'll keep going in the next video.